So I want to what I want to do now is start talking about what happens when we change Morse functions or change the flow gradient vector fields and so on, how handle calculations change. So I don't want to spend, this is not really a course on 3 and 4 manifold topology specifically, so I'm not going to get too far into that. I do want to prove some general theorems in that setting, but so anyway, but there's one thing I mentioned last time that I botched that I wanted to explain about four manifolds. But we start with a 2-dimensional example, and this is supposed to be a schematic here. So suppose you build a 2-manifold by taking a 0 handle, which is nice, easy to draw in these dimensions, and then you attach a 1 handle. You might attach it like this, right? Then you might maybe attach that 1 handle there, so it's along a 0 sphere like that. You might attach another 1 handle like that. Random example, and maybe attach another. Let's be brave and make things non-orientable as well. Attach another 1 handle like that. So here are these different. There are 3 different 0 spheres with different framings along which I've attached 3 different 1 handles. What I want to observe is now we have a 2-manifold with certain embedded circles in it. Okay. And the circles are, I take this, well, let's look at this 0 sphere. It bounds a 1 ball in the boundary of the 0 handle. That's the 1 ball that goes here, but in order to keep things clean, I want to push it into the interior of the handle a little bit. So there is a 1 ball in the interior of this 0 handle that this 0 sphere bounds. Notice that this one also bounds a 1 ball, and this one also bounds. It's all kind of trivial, right? But then the point is that these 1-dimensional balls can be completed to 1-dimensional spheres, S1s, by extending them to the cores of the handles. So then if I attach on the core there, and this core here, now my red and blue mean different things that they've meant in previous contexts, right? Now I've got 3 different circles embedded in this 2-manifold, and those 3 different circles, each one is made out of the core of a handle and something that the handle attaching that bounds. And so this is a general principle that can work in arbitrary dimensions. Various things to observe then are that the fact that these 2 0 spheres are interlocked on the boundary implies that the circle I construct will then intersect at a single point. Okay, so the linking, and this phenomenon where I have if I call this 0 sphere A and this 0 sphere B, then we say that A and B are linked. This is the low-dimensional analog of things being linked like this. Okay? And the best way to say it is that, again, just as we talked about, a embedded sphere can bound an embedded circle can bound an embedded surface. Here I have an embedded 0 sphere bounding an embedded 1 manifold in here. And then these 2 embedded 1 manifolds, well, getting them to intersect here is kind of tricky, but if you push them into the interior, they are forced to intersect. They cannot not intersect. And that's one phenomenon, one way to think about what this linking means. So A and B are linked, and some linking of attaching spheres is intersection of the intersection of the attaching spheres in the boundary of X, let's say, give intersection of the resulting. Well, in this case, they're spheres, but they might say the resulting submanifolds here X prime. So X prime is X units handles. So And so what do I mean by these resulting submanifolds? These are the submanifolds which are obtained by each of these submanifolds equals core of handle union something bounded by attaching sphere. So that's the first phenomenon, that there's somehow linking. And so the exact same thing, I'll do my best to describe how that happens in dimension 4 shortly. But the other phenomenon that I want to point out is this, what's going on with framing here. So I can, let's look at this circle here now, right, which goes over the twisted handle. And let's try to make a parallel copy of that circle inside the surface. So how do I make a parallel copy? Well, this handle here is ball across ball, and the core is ball across 0, right? So let me take ball across some point close to 0. What does that look like? That'll be, say, this. Let's take a parallel copy like this. And pop out this side. Okay? And now notice that you're really seeing the framing here. The fact that the push-off is displaced here. If I did a parallel copy this way, right, then the push-off is on opposite sides. Here the push-up are on the same side in some sense. Okay. Now let's try to extend. So now that's just a parallel copy of the blue part. What about a parallel copy of the red part? Well, in this case, that's easy to do here. They just push off, and the original sphere does not intersect the red sphere, right? Okay. But if I try to do it here, I can take a parallel copy and try and extend this parallel copy, and suddenly I'm on the wrong side and it doesn't connect up, and I have to go cut across there. Okay? And so one way to say it is that this push-off is actually linking, so another way to do it would be to try to connect. I could draw it like that, or I could go, this red here, and say, well, here's my push-off in orange, and I want to extend that into the interior. And so to do it, that also will bound a disk, and that disk necessarily intersects this disk. And that intersection is precisely the linking between these two spheres. Okay, so here I have, because this was a non-trivial framing, I ended up with this, what you can think of as you like to think of it as this circle intersects itself. But what it really means is the circle, when you push it off itself a little bit, is forced to intersect the original thing. And that's called self-intersection number. And so that happens in higher dimensions. And so, well, I want, okay, so I can say, for example, this is what I was trying to say last time. Now if I do a 4-manifold, so I'm looking at the boundary of the 4-ball, say I draw an unknot with frame +1. What that means, so the unknot bounds a disk, right? I take this D2, and I push into the interior of the 0 handle, entirely analogous to what I did there. And then I attach a 2 handle along there, and I take that union, the core of the 2 handle, which is also disk, and this is a 2-sphere embedded in 0 handle and 2 handle. And if I take an analog of this, if I take the push off of, so if I push this off in the 2 handle, in other words, this core, what is this core really? This is B2 cross 0 inside B2 cross B2, and the push off should be B2 cross some point P not equal to 0, right? Then the whole deal is that that push-off is precisely just what you get by looking at it. Remember, we're attaching with the trivialization, right? So the attaching map is trivialized as S1 cross B2. And so the boundary of this, like the boundary of that, equals S1 cross point with respect to the attaching trivialization. S1 cross point is like S1 cross B2 with respect to the attaching trivialization. In other words, we're attaching along a solid torus, but it's trivialized, it's identified with S1 cross B2. And so the attachment trivialization here is +1 framing, which means precisely that it intersects this ciphered surface once at some point. So you get this intersection here. And so one way to think about it then is you can take the disk in the interior and the sphere on the outside. You can try, if you try to push the disk in the interior off itself, if you push the disk in the interior off itself, it would look like this, parallel to it. And well, you could actually even see the intersection right there somehow. When you try to go from one to the other, it's not right. When you try to get from the blue to the orange, you're forced to intersect the white, and the white is the original surface. So all of this implies that you get this implies that you get a S2 in let's call this four manifold X that you're building. You get S2 in X with self-intersection. In this case, +1. It's +1. Why? You got to think carefully about signs. All the orientations work out so that the linking number is actually exactly equal to self-intersections. Now, it's not always a sphere, precisely because you might, in this dimension, any S1 bounds, well, there's only one compact connected one manifold anyway. The compact connected one manifold with boundary as the interval. But if you're doing the four-dimensional setting, you might attach a long knot. And so if you attach a long knot, I shouldn't always draw. Well, it's bad enough to always draw the trefoil. It's even worse to always draw the trefoil the same way. At least this is a trefoil that we can draw a different way. So if you attach a knot, say here with framing +2, right? What that means is this gives X4, which contains a surface, sigma, which is built out of the ciphered surface for the knot, pushed in a little bit, so U equals the ciphered surface, pushed in, union the core of the two handle. And that's a closed surface. Now what you might, I'm just saying push in. What do I really mean by push in? Okay, the ciphered surface has a collar neighborhood on its boundary, right? It's a manifold. Take a collar neighborhood on its boundary. The ball that's on the boundary of has a collar neighborhood on its boundary. I can then use a bump function to sort of, use a radius function to literally I push it in. So these points in the interior, away from the collar neighborhood, will be pushed down. Instead of being radius 1, they'll be pushed into radius 0.9 inside the ball. And then along this collar, as I go in, I change the radius from 1 down to 0.9 using some kind of bump function. Something like that. So that there's some consistent way to push it in so that it becomes transverse to the boundary and meets the boundary along this edge. So this surface then would be a smooth surface. Actually, what you really want to do is have this sigma, when you push it in, come in and hit the boundary at right angles. So that when you attach a handle, you actually get something smoothly embedded. All that can be worked out. And then the self-intersection, which is often denoted sigma dot sigma, so self-intersection, this is really what you get when you push sigma off itself, will be, in this case, +2. It'll be whatever that framing is. And then the other phenomenon that can happen is this linking phenomenon, where if you have the linking phenomenon, if I attach two different two different two handles long, whatever, doesn't matter. If I attach I call this A and I call this B, this will give in this case, two disks. Each of those knots bounds a disk, which I can push into the interior, and then I'll have two disks pushed into the interior, each of them capped off with a disk in the handle. So I'll give two different S2s in in the interior, in X, in the 4 manifold, and those two S2s necessarily intersect, because if you push this, somehow this just takes some staring and thinking on yourself, on your own, to see that if you take two knots that link like this, and you take their cypress surfaces. See, the cypress surfaces in R3 intersect, along an arc or something, but you want to push them into the ball so they intersect at a single point, and then these two S2s in X, which intersect once, intersect transversely at one point. Yeah, I don't know for how many of you it's sort of easy to believe that two-dimensional objects intersect in a point in 4-dimensional space. For some reason, it took me forever to really believe that, even though I could do linear algebra. You do linear algebra, right? R2 and R2, the XY plane and the ZT plane intersected at 0, 0, and that's it. But for someone that likes 4 manifolds, it would be surprisingly wrong to really believe that. But I think I sort of believe it now. Okay, so that's all at once. So somehow from these diagrams, which we're going to talk a little bit more about, these are pictures like this are sometimes called Kirby diagrams for 4 manifolds, sometimes called framed link diagrams for 4 manifolds. From these diagrams, you can read off a lot about embedded surfaces inside the 4 manifold. One other thing, I guess, to say, what if one of these goes over a 1 handle? Okay. If you have something going over a 1 handle, then suddenly there isn't a surface that it bounds necessarily. And if there isn't a surface that it bounds inside the boundary, it won't extend. So if it represents a non-trivial element of H1 of the thing you're attaching to, you've got a 4 handle, a 0 handle with some 1 handles attached that has non-trivial first homology, and then you start running stuff over that. If you're going to represent non-trivial elements of homology, you're not going to bound anything, and then those don't produce closed surfaces. That was sort of to finish the topic. I didn't explain very well. I may not have explained it that well here, but hopefully you get a little more intuition. But what I want to do is back up now and think. So somehow we have this picture that Morse functions give handle decompositions, which gives us sort of a theorem that says that any manifold can be built out of handles. And there's actually a slightly subtle question, which is, what do you mean? Can you go the, of course, you can go the other way. Given a handle decomposition, you can produce a Morse function on it. But there's a little bit of subtlety in terms of thinking about exactly what Morse function you want to produce. The real issue is which handles are attached first. So you have a bunch of 1 handles attached. I'm going to give a simple example. Going this way is not entirely trivial, but the main issue is, suppose I build a 2 manifold by attaching a 1 handle here and a 1 handle here. What should the level sets look like? Say I want to say that came from a Morse function. Well, I can say, okay, great. First I have critical point index 0 in the middle there, and now I start expanding, so I'm going to draw the level sets. Now the key thing is, if this one's attached first, then you're going to start to have level sets go up here. I didn't leave myself enough space to make this picture work. And then eventually, just try to and then I'll have another space, I'll have a level set that comes in and crosses. And that's all happening before I've done anything to this one. And then after that, I would have a level set that comes up here, and goes around, and then finally I'm crossing there. And so this would imply that I have a Morse function where this index 1 critical point is below that index 1 critical point. And you could, of course, have the other situation happen as well. And just from the handle decomposition, that's not a problem. And sometimes it's important to keep track of those things.
You could do it, I guess if you did it, sort of one level set that
Has both.
has both, that's like self-indexing.
Yeah, that's like a self-indexing Morse function. And of course, you could do that, but you may, well, I'll give you, we'll shortly, the claim is that you can't, the real issue that I want to say is that if you have two self-indexing Morse functions and you want to go between them, you can't keep them self-indexing and Morse at the same time. And because suppose you want, there's what we're going to talk about soon is what's called a handle slide. I'll give you intuition. If you want to take this handle and slide it over that handle, that should be somehow not change the manifold. To do that, this critical point has to be higher than that critical point. And so if you want to keep all critical points at the same level, all critical points at the same index at the same level, you can have problems. Okay. But I want to talk a little bit more carefully about how this direction works. Okay? What I said first is, the original thing we said is you take your big manifold and you cut it into elementary coordinates with one single critical point in each level set. And then you say each piece, you then say there's a product using a gradient vector field, and then you go really close to the critical point so you get into a standard neighborhood, and then you find the handle there. So you say sort of big product, little handle, big product, little handle. There's a slightly different way to do it. Well, if you think about it, that's not how we're really visualizing this. We're really visualizing this as just one thing and then handles coming down far. So what I need to do now is introduce the notion of ascending and descending manifolds. And if you've done any dynamical systems, these are the same. These are what dynamical systems people call stable and unstable manifolds, except I don't know which one is which. And it sort of depends upon which direction your gradient vector field goes. And I never remember that either. I think gradient goes up. So you can probably figure out which one is stable and unstable. But here's, so let me try to actually define something. So given given a Morse function, f from manifold x r, or to r to an interval, right? Let's stick in the world of coordinates. Okay? If I write this, that implies x is a coordinate. Right? Then x is a coordinate from n0 to n1. And given a critical point, so first thing we're going to do is choose a gradient of like vector field V for F. So I haven't actually defined what gradient like is. A gradient like vector field is a vector field that arises from some metric adapted to the Morse function. Remember, metric adapted to the Morse function means that in some local coordinate system in which the Morse function is standard, the metric is flat Euclidean metric. That just guarantees that the vector field is the standard gradient vector field. Another way to say what this means is that the vector field V is transverse to the level sets everywhere, and except where it's zero at the critical points, and in the neighborhood of the critical points it's standard. So the transverse level sets and standard in the neighborhood of the critical points. So this is why some people like to say take a metric and you get this. Some people just like to think directly about the vector field. They're really, if you have the vector field up to scale, it can be the gradient of an appropriate metric. You just choose a metric so that vector field is perpendicular to the level sets. Choose a Riemannian metric. So that if you think about it, you can actually patch together using both functions. If on charts you pick inner products that make certain level sets perpendicular to certain directions, you can actually patch those. The set of those such things is a convex set in vector space, and so you can patch those together. And so you can if you had a particular vector field you wanted to be a gradient for a metric, you could choose such a metric. You could build such a metric. You'd have to scale it because a gradient has a particular length. That's the something. Okay, so once you have this gradient vector field, now you're given a point P, given a critical point P. The ascending A sub P is the ascending manifold of P is equal to the union of all flow lines. Oh, I didn't say, let's see, V, gradient-like vector field, let's say V, I just said transversal level sets, let's say V points out. Once it's transverse, then I didn't specify whether it should be up or down, but I think let's just make the convention that the gradient vector field is going to point up. And so it's the union of all flow lines of V with the limit as t goes to minus infinity equals P. So it's all the flow lines which, when you flow back in time, backwards in time, hit P. Okay. And it's that is the union of that union P itself.
So what do you say up? That really means like if you flow,
I mean,
the
that means
function increases?
That means df of V is positive, which means that, yeah, if you flow along it, the more the value of the function increases. Right, so up with respect to the function f. Does that make sense? I always think of Morse functions as a height function, right? So this is like, we should have a picture. Draw a standard picture. Critical point. Right. And it's all those points which, when you flow backwards in time, you take all flow lines with the property that when you flow backwards in time, you get to this point. So that would be. And the descending manifold is the same thing, but all those points which when you flow forwards in time. Okay, so that would be this. Why is it a manifold? We call them manifolds. So the way to see that it's a manifold is, first of all, so a manifold because well, first of all, in the neighborhood of P, these are manifolds. Neighborhood of P, they are manifolds. Why are they manifolds in the neighborhood of P? Well, in the neighborhood of P, they're just, in standard coordinates, they're just the x1 up to xk axis, or plane, and then the xk plus 1 up to xn axis, right? So, in the neighborhood of P with this, this is x1 to xk, and x plus 1 xn, and then our standard model. This is negative and this is positive, so that means that this is the descending manifold P, and this is the ascending. Does that make sense? Okay. That's just these are the points where you flow backwards in time to get to P. These are the points where you flow forwards in time to get to P. Now pour water here, this is where it goes. If you pour water anywhere else, it's the stuff that goes to the neighborhood. So they're manifolds in the neighborhood of P, but then outside the neighborhood of P, right? Your flow just gives you a product structure. Okay, so outside these neighborhoods, the best way to say it is that now outside is just going to be whatever the boundary of this thing is, and then just flows forever. So you're going to continue. It's going to continue to be more of this. So outside the neighborhood, these are just actually what are they're manifolds here, which are so inside the neighborhood, these manifolds just look like bk and bn minus k. This is the descending. This one's the you know what I'm saying. That's the descending and ascending manifold. Outside the neighborhood, the flow just gives you this product structure, so they just become boundary of bk cross some interval, however far you cross it. Or maybe infinity, depending how far you flow, but yeah.
What if they hit other critical points?
So, let's talk about that. Suppose it hits another, well, let's look at, let's take this picture and just cap it off at the bottom, and let's see that we get, make sure we get the, okay, so let's suppose we get that picture. So now there's a critical point down here, and there's a critical point here, and the question is, well, okay, in this case it might actually look like it would be it'd be manifold anyway, but according to my definition, is this critical point in the descending manifold for that? No. Right, so it doesn't ever hit the other critical point. Okay? So when you're flowing, you're really just flowing along a non-zero vector field, right? Because you never get out of. I mean, the only place on this manifold where the vector field is zero is at that critical point, right? So this point is if I call this P minus Q, then Q is not in the descending manifold. Of course, you can hit the boundary, and then you have to think carefully about knowledge, but it's fine. Everything works right. What about the ascending manifold for Q here? In this picture, the ascending manifold for Q is all those points which, when you flow backwards in time, you hit Q. Well, it's all this stuff, right? It's everything except P, right? We don't hit P, and we don't get any of these points on the ascending manifold for P. Okay, so it becomes. I mean, it's definitely not a compact manifold. It has that sort of taken out of it, but it's the in this case, the ascending manifold for P is equal to the whole x minus the ascending manifold for Q is equal to the whole x minus the ascending manifold for P. Okay. But again, it's a manifold. And actually, if you think carefully about it, you can show that it's always
dimension.
So let's write down the dimensions exactly. I sort of implied that, but just to write it down. These are submanifolds, right? And so the dimension of the if P has index k, then the descending manifold for P, dimension of the descending manifold for P is k, and the dimension of the ascending manifold for P is n minus k, and d sub P and a sub P intersect transversely at one point, which is P, and that's a transverse intersection.
Always intersect higher dimensional manifolds transversely, like that they're contained in.
Oh,
Is that?
you can have higher dimensional manifolds intersect non-transversely in a single way. This intersection is transverse.
No, I mean like, is if Q, like DQ is just a
Oh,
point.
I see. And DQ is a point, yes, okay,
So
right.
that's-
Right, what it means for a zero manifold and a zero-dimensional manifold and a two-dimensional manifold, well, you have to talk about the ambient space as well. So if I had in a surface, if I had a zero manifold and a one manifold, transverse intersection needs to be disjoint.
Oh, because it's like a stable thing.
Yeah, it's transversely is what should happen generically. Okay, and so, I mean, really what it means to be transverse is to say that at every point where they do intersect, the tangent space, the sum of the tangent spaces of the two submanifolds should equal the tangent space of the whole manifold.
So you gotta
And so if the sum of the dimensions is less than total space, transverse intersection needs being disjoint. So, but anyway, in these cases, the sum is always equal to the whole thing. So then you expect transverse intersection to be at points, but of course you can still, it is still possible to have non-transverse intersections at points, but we'll find, just again, because the only intersection is this point, it is transverse just because we forced it to be in that local model. Okay. Now, the advantage to the reason I wanted to bring this concept up now is that what it really allows us to do is to sort of make our handles big and long, right? What we would have said first in terms of getting a handle decomposition is it would have said take this large product until you get into the standard neighborhood and now take that little handle. But instead you can take you take your germ of your handle inside this neighborhood and now just flow it down along this descending manifold until you get as far down as you want. And you can say that this whole thing is the handle. So let me write that down more carefully. If maybe I'll try to say this here. Suppose that x has critical points P1 up to whatever M, right? So a whole bunch of critical points, and suppose that the okay, so yeah, there's one other thing one other example I wanted to do to illustrate this point first. I could also cap these off, right? And put critical points up here, right? And in this case, you see something where the descending manifold for this critical point really does sort of get broken somehow at this point, right? And so I sort of think of the descending manifold as being like a disk where part of it stopped here, right? Although really, if you could parameterize it just as an open disk, right? But what I want to do is suppose that the descending manifolds so another way to say that though is that really what's causing this descending manifold to run into that critical point is that this descending manifold and that ascending manifold intersect. Okay? And if that doesn't happen, then this descending manifold would sort of extend all the way down to this level. Right? Suppose the descending manifolds and descending manifolds, maybe I should write it this way. D sub pi intersect ascending manifold for pj are disjoint for all I and j. Okay, so I've got all these critical points, and none of the ascending manifolds of one hit the descending manifolds of any others. Right? Then I claim that then X can be built 0, 1 cross 0 union by attaching the handles for all the critical points, P1 to Pn, all along 1 cross 0. Attach them all at once. So the idea here is that this, as long as your descending manifold extends all the way down to the bottom, right, without getting hung up on anything, then you can take this little handle structure here and just extend it all the way down. So maybe the all at once. And so the picture somehow is like if you have something like critical point, and another critical point, then this descending manifold here comes down, hits, and then this descending manifold comes down and hits. And then you've got the two different handles structures right there. One of your handles and the other handle. And you can attach them both at the same time to interval across the bottom. 0. But if you had some, if you instead you had this picture, for example, then sure you can attach these handles at the same time. But this handle now, it cannot be attached. You can't attach it before you attach this handle as it goes over. And that's the intuition, and I won't belabor the technicalities. I think the idea is pretty clear. But if you wanted to write it down very carefully, you'd have to say, I take this the beginning of the descending manifold inside the standard neighborhood. I see that its boundary is I take the beginning of the handle itself. And see that the handle is a thickened up descending manifold, and then I just see that because I don't run into anything else, then for a small enough neighborhood I can flow all the way down to the bottom. Okay, so the moral is that the handle really equals thickened descending manifold. Okay. So now I want to investigate the question: under what conditions do we expect to be able to keep ascending descendant manifolds disjunct?
Oh, sorry. When you say the handle is a thickened
descending,
so in this case when you have that like index 2 critical point, isn't the thickened descending manifold like a little cylinder?
No. Well, thickened inside the ambient manifold. So in this case, thickened. Thickened means thickened means crossed with a disk, so that it crossed with a disk of the right dimension, so that it ends up having the dimension of the total ambient space. So this case, right, the descending manifold is a B2. Well, this is a 2 handle. 2 handles B2 cross B0. Why did we bother to say B2 cross B0? Because it's consistent with everything else. But when I have a minimum, right, then the descending manifold is a point, and then it's thickened. Right?
By a V2.
By a V2. So I always think of this small, or let me say that it's a small tubular neighborhood. So you can also say that another way to state this, maybe perhaps more precisely, would be to say that if this condition is satisfied, then the x is. Then you can take x, you can take a collar neighborhood on the bottom, and then you take a tubular neighborhood of all the descending manifolds, and the complement is your product. So you could say that x, actually you could say this, maybe more formally, in this condition, I don't want to try to write proof of this down, but I can write the statement a little more carefully. You know, in this case, where all the ascending descending manifold is disjoint, X is actually diffeomorphic to a collar neighborhood on M0 union tubular neighborhoods of all of these CPIs. All the decision neighborhoods. And with smooth corners, right? If you take a collar neighborhood union tubular neighborhoods, you'll then have corners, right? If you do this, collar neighborhood, union these tubular neighborhoods, you then have around these corners. And then the claim is that that's not the whole manifold, of course, but it's diffeomorphic to that, because I think the argument should be similar. So when is I, J, can't be said. Oh, we're going to do dimension count. But this is slightly confusing. The best way to do it is to say, you know, first of all, the only way the descending manifold of one could intersect the ascending manifold of the other is if this one is below that one, right? So first of all, you need when is it not even intersect?
Just as maybe it's a very simple question, but just that descending manifold of the blue one there,
Yeah.
where does it intersect the red one?
It doesn't intersect the red one. It intersects the ascending manifold for this, right? It intersects the ascending manifold for this point,
I see.
and it intersects along this entire arc. But what we're going to do instead, rather than think about this intersection of the arc, we're going to think about the intersection of level sets. Okay. So I don't know how I want to state the question. When is it equal? When is it not equal? Oh, let's say when is it equal? All right, change your mind. Okay. So first of all, if remember the descending manifold is always below the critical point. So if f of pi is less than f of j, then it's obvious. Okay, because you can't have, there's no way you can do it. It's obviously equal to the empty set. Okay. If f of p, so let's consider the case where f of pi is bigger than f of pj. Let's consider some. Let's look at the simplest case. Suppose no. Let's just. Simplest case is that no critical values in between. Just to make it easy to think about. And then.
You can reduce to that?
Well, yes, because, well, I'll talk about that. Okay, I mean, maybe the best.
Is that the same statement as?
It's not quite. I can't quite immediately reduce to it, but I just want to avoid complication. I think you can figure out how to do the case for this radicalizing between. What I really want to say is it doesn't. You don't. I want to look at the sort of the first possible place where there's just suppose I'm looking at two critical values, two consecutive critical values, and I want to see it is still a special case. I have two consecutive critical values. I want to ask, is it possible that the ascending for this intersects the descending for that? Okay, and so then what you do is you look at take some regular value, say y between f of p j and f of pi, and then consider. So what do I have? I have f of pi, and I have f of j. I mean, I have pi in my manifold. I have pi and pj below it somehow, and then I have this level set, and I want to consider f inverse of it. And then I'm going to have a descending manifold that just draws schematically like that, and an ascending manifold like this. And so consider the descending manifold for pi intersected with f inverse of y. And let's call that let's call it the descending, I'm going to call it the descending swell. I'll just rewrite that. And the ascending manifold for j intersected with f inverse of y. So the first thing is, knowing that I don't have any other critical values means that this descending manifold has not already crashed into some other critical point, right? And so once I know that, that means this descending manifold is just a disk, a ball of some dimension. This is a ball of complementary dimension, and so this is diffeomorphic to a sphere of dimension. This is a dimension equal to the index, so let's say ki minus 1. And this is diffeomorphic to a sphere, the boundary of this length, so that's the asymptotical n minus kj. And so, well, I don't have time. I'll finish this next time. But the point is then to just count dimensions and think about generically where you expect these things to intersect or not. And what we want to do is argue that you can always choose your vector fields so that all these intersections are transverse. And if they're transverse, then you can figure out conditions on these indices to arrange that they should always be able to be made at this point. But we're